Yes. So I will be doing something on linear functions later, but I think let's continue with this thing on area, right? Yeah. So we were looking at what? We were looking at area, or rather I should say length, to be more familiar, length of sets or just subsets of R, lengths of subsets of R. Okay, so the definition, a rough definition has been given for this, right? So let me not repeat the definition. Let's just directly jump to the problem, right? What is the length of Q? If anyone has tried. And if you want, I can review the definition. I've given a very simple definition. The actual definition is complicated, but we don't need it. The simple can be given and asked questions can be asked. You can also guess if and so on. If you have not tried it. Concept of length. Yeah, so area in R, I'm just calling it length in R. Okay, so let me say that concept. So the idea, the reason why I'm doing this is I don't want to go into the theory of length of subsets because that's actually a very complicated theory. But this simple definition of length, simplified definition of length, which I'm going to give, can be just given and questions can be asked. So let me do that. So I should write actually, because later on you will learn the precise definition. But right now I'm giving a simplified definition. It's not a vague definition, but it's just simplified. Simplified definition of length of a subset of S in R. Sorry. Well, first of all, the idea. Okay, idea I'll just say because we have discussed this last time. Well, the idea is to take a subset of R and assign some number to it, right? What is the rule for assigning the number? Is that we are going to first start by assuming that the unit interval has length 1. Let me just say L, it's just a function. The unit interval, right? This has length 1. And if you translate it, length remains the same. If you expand it or contract it by some amount, twice or thrice, then the length will get multiplied. And these things, obviously, right? We want this. Now, these will be given as axioms, maybe 1, 2, 3 points, but these are very simple. That's the first thing. So then with this, so far, we are able to assign lengths to intervals, right? So L of intervals, we can make sense, is fine. And all of us know this. Now, how do you make sense of this concept for sets which are not intervals? That's the next thing, right? So maybe I'll color. Now the task is extending the definition for non-lengths. Okay. So obviously, if this is given as a problem, only the properties will be given and you have to make sense of them like this, that, okay, first two properties are defining it for intervals, next two properties are extending, then only you can solve the problem, because just knowing the properties robotically will not help you to maybe solve the question, right? If it's a good question. So extending the definition for non-lengths. Now this is meaning that for a general subset S, for for non-intervals. And this will be similar to what we did for shapes in R2, right? When you had a shape in R2, we said roughly that you approximate it with squares, right? So unit squares or small squares, and then you kind of that sum of those squares will roughly be the area, and you make it smaller and smaller, the number of, yeah, you approximate the set better and better, right? So that's the idea we're going to use, is by approximation. So for this, we will use approximation, using approximation. So we will basically be taking a set, we will be covering it with intervals, and then take the best smallest cover. Okay, so you start with a set. Okay, you cover it, you fill it up with intervals, cover it with some intervals. Let's take just like this. So you can have in R, you can have a set. One second. Okay, no issues. Yeah, so we have just started, so not a problem. This, and then you're going to cover this with intervals. Okay, right, and this cover, okay, this cover will give you a length, right? So this will imply a length L1. Okay, what will this length be? It will be the length of the sum of the covers. Okay, this length is equal to sum of the length of the intervals, I mean cover intervals. This will be the length. Right. Now, what should we define as the length of S to be? From here, can you further extrapolate? So if you take, absolutely, yeah, exactly, because we are going to approximate. So we're going to take better and better covers. For example, this cover that I took here, you can obviously, you can see, it's, you can just, that you can make it better. For example, here, clearly we could have taken the smaller things, and this would be a better cover. So you're going to just take the minimum uh, or infimum, same thing, but you would know what it is going to be, minimum or infimum, whatever. Doesn't, you don't need to know the exact definition of infimum. You can just take, yeah, just take the, where I, uh, this is a bad notation, some, okay, a kth cover, yeah, because there can be many different covers. Okay, this is, now this is not a complete definition. Okay? A lot of things are missing, but whatever I've said is precise, and this is enough for us to answer this question. So anyone has still doubts about what the definition is? More will be cleared when we do this question. Okay, if there, okay. So now let's do. Anyone has any idea? Has thought about this? No idea? Then let me make the question a little easier. Yes, good. Yeah, good question. Yeah, and that's what I was going to. That's a good thing to think, right? What should be the length of n? Sorry. Yeah. Anyone? What do you think it should be? What? Okay, so try to understand this, that this length is relative to the reals. Right? When you say as a subset of R, it means that it's relative to the real numbers. So relative to the real line, what is the natural numbers? What is the size of the natural numbers? Relative to R. Exactly. You see, when I just said it in this phrase, the answer was clear. Maybe it was clear before also, but it becomes more, right? It's the same thing, but what it is really trying to capture is relative length, size of n relative to r. This is what area is all about, right? You start with an interval, you assign it 1, and then relative to that, you do everything else, right? So size, now can anybody make it precise? Size of n relative to r. Now, all this I'm giving the motivation, but if this the definitions is given in exam, then you have to figure out motivation. But this is a practice that has to be there, trying to understand what it's trying to say. It's trying to say in different ways. Yeah. So the answer is 0, and that's correct. How to prove it? Mhm. You have to make it. What you're saying is, if you should make it more precise, because length of any interval will be more than 0. But yeah, cover it. Uh, you should. Okay, but you can cover it, right? You can cover it. So what you're saying is formally wrong, but you're getting to the idea. I mean, if you have to prove it, it is 0. You have to just try to cover it with smaller and smaller intervals. Just say smaller and smaller. Hmm. But you have to but you have to cover everything. Yes, but you're right. You're getting to the idea. But you see, the task is multifold. Yeah, you take this cover, and but this is not a cover. This is just covering the number 3. So what you have proved is that, so what Chandan has said, that proves that the length of a number is 0. Okay, but we want to show that the length of all the numbers combined, this has to cover the set n, has to be, you can just imagine tends to 0 if you want. But this is the fundamental idea actually. And it is actually just an application of something very simple, which you have all of us have done. But yeah, it's hard to guess maybe. If I just give you a hint, then you can do it very quickly. Yeah, but what should be the cover? Yeah, limits will definitely come in, but that will just be just yes, certainly, yeah. But that will just be but that will come at the level of a formalism, just to formalize something. But guessing what covers you should take is is a, but because, for example, if you take covers like this for every number, right? So if you say, just giving an example, that how should I write it? Yeah, I just write it. And this will not work for the natural numbers where k is going from 1. So this has covered the natural numbers, and this will not work because even when you take n to 0, right? Right. So you get so suppose this you're calling ln, okay? But ln does not go to 0. The length of ln, right, does not go to 0, right, as n goes to infinity. So all this is rough notation. Because even when n goes to 0, infinity by n doesn't go to 0. Or, yeah, infinity times n, sorry. Infinity times 1 by n. Yeah, but 2 by n. Yeah, but that is not, will not go to 0, right? Just think. Because you have to add it. No. But the natural numbers are, but the natural number n is same. Right. Right. But you're getting to it. Yeah, you have to just think a little more. Okay. So Raghav, what we are doing here is just the problem that we started with last day. But just to put it just as a problem simply is that we have the natural numbers. We want to cover it with open intervals or closed intervals so that the total size of the cover can be made as small as we want. So the key statement is here. That's the challenge. Okay. So I will just expand this one a little bit just so you can become more sure there's no confusion. Because if you take meanwhile, you can think if you're comfortable with this, but I'm just writing. If you take this, then the length of this above thing, okay, length of above is equal to 2 by n plus 2 by n plus 2 by n, right? And this is not going to 0. It's actually infinite for any n. For n equal to infinity is not, no, there's no such thing. Every natural number is. No, but even if n tends to infinity, this goes to infinity. Summation goes to infinity, doesn't go to 0. And that all of us know, the concept of limits, everything. Right? It obviously. No. Think. No matter what the n is, this will be infinite. For any n, it's exactly infinite. It doesn't come down at all. Right. And maybe what Chandan was saying, if we do that, I just want to show that that will also not work. Like if you take the interval smaller and smaller, or maybe I just take, yeah, you can take 2. And then you understand 1 by 3 by 4. That also does not work. And you guys should know the reason. 3 minus 1 by 3. Yes, but it will not work still, right? Yeah. But if you take the length of this new thing, this new C, right? This also does not work because now the length, though it is decreasing, you have 2 plus 2 by 2 plus 2 by 3 plus 2 by 4, right? You see, but this also is infinite. And we know this harmonic series. Yeah. Yeah. Infinite GP is the answer. Though, I mean, you have to still complete it. Yeah. Yes. Right. That is kind of, will get to the answer. Right. So you see, when you make this, when you do these mistakes, then only you see the right answer. That, oh, okay, it's just about series summation. Okay, and this comes up in this just, I mean, I'll just ask a problem integration also just now with that, and you can think about it for homework. It will be maybe slightly more complicated. So this, and then, yeah, so this works, it's right. But yes, this has to still be adjusted. but you guys see the point. But so the length, but you see the length of this particular cover. Okay, so let's call this cover G, yeah, G1, because this kind of geometric series and one is there. Yeah, the length of G1, what is the length of G1? It is 2, I think, roughly 2. But this is still not going to 0, but at least it is not infinite. So what more should we do so that the length actually starts going, so that the lengths of these covers start going to 0? It's not yet done, right? The length is 2. Mm-hmm. Mm-hmm. Yes, exactly, right? You just put an epsilon here and you will get 2 times epsilon here. Something like that, right? You can do. Or you can take 3 to the power also. It's up to you. Like 3, 4. Anyways, you can make it as small as you want, right? So when you take these covers, then you get it. And you can just think this was not so hard if you look back. Exactly. Exactly. That's a good way. That's important to put like that. Yeah. Given epsilon greater than 0, can produce a cover. This is obviously just a part of formalism. The real thing just came that we wanted to make it smaller and smaller. But yeah, but we should write this. Given an epsilon can produce a cover C whose length LC is less than that epsilon. You see, so it means basically that the infimum or minimum, whatever you want to call it for now, goes to 0. Okay, so that was the thing. Now I'll just give a 3 problems based on this kind of idea. Okay. So obviously you still have to do this homework. Find the length of Q. Don't think about, no need to think about this now. Take your time and try it later. So you see these problems are very elementary. Okay, but such new flavor. Find the length of Q, and based on this, yeah, I can ask this. Find this, so you're finding this length of Q in R. Remember, because your primary starting point is that length of unit interval is 1. Based on that, you are doing your work. Okay. Now, if I ask you, find the length of, I mean, not find, but you know this. This is the axiom, is 1. We know this. Length I should write. I just want to basically extend upon the concept of relative and ask this question. Find the length of R in R2. So what does it mean to find length in R2? It means you have to cover it with squares, okay, or balls or squares, tiny squares. Because for each square, you know what the length is. You have to cover it with squares so that the sum of the length of the squares is smaller and smaller. Okay, so try this. Fine. Then you will understand this concept of relative better. Okay, and these things go a long way into dimension and so on. So do I want to say anything more in this? No, for now, let's not go too much into this. This is fine. Any questions? Okay. Now let's move to the next thing, that is length of I had defined a process last time. Today, let's give it a name. It's called the Cantor set, length of the Cantor set. Or you can also read more about this, but we will only do the very elementary one so that you get an idea. That's more important, an intuition about this thing. Right. So where to start? Let me just quickly define the Cantor set once again. And today I will not define it in a very nice way like we did last time, but just say it quickly. You are just taking the unit interval. You're deleting, and this is how it's called in textbooks also, delete the middle thirds, middle third, right? Delete the open middle third. This is deleted. Deleted. You consider the rest. You get the rest. Now from the rest also you do the same thing. You delete the middle third and consider the rest. And yeah, so in this way you go on. So you're getting many intervals, but the size of the interval is getting smaller. So what should be the length of the Cantor set? And then the final thing that you get is called the Cantor set. The numbers remaining, or I should rather say numbers that never get deleted. The numbers that never get deleted form, I mean, they are defined to be, they are called the Cantor set. Let's call this, this I think is denoted as C. So C1 was maybe 0, 1. Maybe I should call this C0, but or maybe this is okay. Then C2 was, if write it like this, and similarly you can understand. What will this be? Yes, that's what. But then the number of intervals, yeah, actually it should be C0. But yeah, I'll change it. Maybe 7 by 9. This is. So this is just an alternate way to write things. Now what am I doing? No, it's okay, right? 6 by 9 and 7 by 9. And then 8 by 9. And then yeah. Yeah, so maybe in the step number or whatever you can say. It could be just written C infinity here. This is actually an easier question than the previous one in some sense. But the set is a little new maybe for you. But the question is actually simpler. This is the same thing which I'm using. Mm. 2 by 9 comma 3 by 9. It should be 3 by 9, right? Sorry. Yes, right. Absolutely. How can it be 1 by 9? Yes. So, yeah, so you would know that it's kind of going like this, decreasing. Or just see whatever. Here you can use the properties of length, or in some sense the covers are already given to you. Yeah, those are the things. Actually, problem is actually this answer is in front only, but it's a new setting. It is zero. It is zero. Right. Uh, certainly. Right. Can you explain? It's 4/9. Right. And you can give a very simple reason, right? Yeah. Yeah. Absolutely. Yeah, that's correct. That's right. That's right. That's right. You see, at the kth step, this will be the length, and there's a very simple reason. You can, if you don't see it immediately, you can do it by calculation, but try to see it. It's a very good reason why this is true. Or it's 3 to the power. Yeah, obviously, yeah. But seeing it, induction you can use to prove it, but just to see it, right? Like at the kth step, there are 2 to the power k intervals because you're dividing at each step, and the sizes of the intervals is, getting divided by 3 at each step. So it's, you understand, will be okay. So basically, each of this ck is a cover for c, right? Each ck, if you want to say it in the language of covers, each ck is a cover. I mean, it's a closed cover, covering by closed intervals, but that's fine, right? It's a cover for the final thing. So actually, everything is in front. It's just given to us, laid out. There's no new construction here. If you assemble the things, each ck is a cover for c or c infinity, whatever. Maybe c infinity is a very bad notation. I shouldn't use it because it means other things in maths. It's cover for c. Each of it is covered. So actually, the smaller and smaller covers are actually given to you, and yeah, very simple question actually. But so, are there any questions with this? This was very simple. Okay, but why I did these two examples is obviously these are some good simple problems to do, where to see the definitions and we do the problem. But theoretically also there is a very interesting thing happening. This will actually help you to understand the kind of thing length is. Okay, what do I mean? I mean that the Cantor set, this set and the rationals, both, I mean, the rationals you will prove, mostly you already understand that the length of this thing that we have seen here, this iteratively generated thing, I mean, this comes through some processes, but will not now. The length of this and the length of Q, the length is a notion of size, right? The length is a measure of, in some sense, it's a measure of size, right? But like a non-geometric size, it kind of tries to capture size, but in a volume sense, in a quantity sense, right? But not in a geometric sense. Okay, and also not in a set theoretic sense, because we're covering it with intervals. But that last thing maybe is not clear until we do this example, in the sense that you can prove that the size of Q, the size of C, this Cantor set, the size is the same as the size of the real numbers. And the size of Q, you know, is just countable, is same as the size of the natural numbers. Obviously, these things have to be proved. What do I mean by size here? So this size is in terms of bijection, that there is a bijection between C and R, and there is a bijection between Q and N. In that sense of size, they are very, very different things. But both are senses of size, and they increase kind of as set becomes bigger and so on. But still, they are very different here, but they are same here. You can make what you want to make out of it. Okay? But this kind of says that these two are very different notions of size. It's not like one is, you know, something. But this we will not prove now. It's not needed for us. But this can motivate you to do this problem, which is elementary and just involves some number theory, maybe a little bit, and it's, you'll see. Not number theory, you'll just try it. So describe the numbers, describe C, describe the numbers in C. The numbers in C by going to a different base. In base 10, there is no good description, right? But you can imagine, you know, that there may be a good description in some other bases. Let me just give you a quick thing on, it means a quick way to see base 10 in a way that Cantor set is. Okay, if the Cantor set is constructed. So if you take a number in base 10, let's say you take a number like, let's take any number, doesn't matter, 5, 1, 9. Just take this number in base 10. Okay. Can you describe this number as a subdivision process like is done here? Okay. And it goes to the very definition of things. Basically, we know you have the 0 to 1. You're going to divide it into 10 parts. Okay. And then you are going to, if you want to find out this number, then what process similar to this will give you that number, right? Just as the first step, that this number is in the first interval, right? Is in this interval. You can remove the rest. And then again, you can divide this into 10 parts, not 3 parts, but 10 parts. And then you pick the second block and then again divide that into, you get it. I'm not saying more because otherwise the answer will be given. So any number in decimal expansion can be seen just taking and subdividing and further subdividing as an iterative thing. Cantor set is defined in a similar way. Now, can you combine this to give a good description of Cantor set? Because still now we don't have a good concrete or rather constructive description. We have a existential description, intersections and so on. And that after that, there is only a small step to prove that it is uncountable. But we don't need to do that one. So try this question. You can just take some examples also and see what kind of numbers you get to guess the base and so on. Try this. We will discuss this because this may not be trivial. So now let me give another problem based on the ideas we have so far. Okay. Yeah, no, so decimals are already in base 10, right? The decimal expansions that we have, for example, if you take this number, right? Now, what is this number? Right? This number is basically, oh, yeah, exactly right. That's what it is. And so I'm saying that how can you find it by an iterative process? Right? So you take the unit interval, you break it into 10 parts, and you pick the second one, right? And you see, you're sure that this number will lie in this, right? Between 2 by 10 and 3 by 10, right? 0.213 will lie in this, right? Certainly. Because it's not more than 3 by 10, right? Otherwise, this would have been 3, right? So you take the unit interval, instead of dividing into 3 parts, you divide it into 10 parts, and you find the number in that. But how you're going to locate it is, again, you're going to divide this into 10 parts. And you're going to, because it's 1 by 10 square, you're going to pick the first part. And you know inside that, you'll get this number. All right? And then you further do it. Take a number and try to describe it. You will understand. Okay. Yeah. Is that did this clarify anything more? Or no? Then I try to say it again. Okay. Yeah. I'm trying to not be very precise, otherwise the answer will be given. Yeah. But this is just this. Yeah. Okay. It's just an approximation thing, right? Further and further. Okay. So then let's go to another question, which we'll not do today, but we have to think about. This is based on the ideas we've done so far. Maybe, yeah, in terms of functions. Okay. So give an example. I'm already telling you that it's there. Give an example of a function f from R to R, so the reals to reals, okay, which is unbounded. Okay, but integral, and here you don't need to, I mean, all of you know integration, I know, but I'm just saying that you need to know integration only only that it's area. Okay. Such that I should just say area under the function, but yeah, integral of, just to be saying that I'm doing integration, maybe this is finite or 0. But if you think of a function, continuous function, yeah, that's where integration comes in, right? Think of a continuous function. Otherwise, this will not make sense. It will, but yeah, let's think of a continuous function. F is continuous. Now, this is something that you can try. Even a differentiable function is there, but think of a continuous one first. See, so now unbounded, you understand what it means. Unbounded means that for any m, there exists a x naught such that f of x naught becomes bigger than that m. So it just becomes bigger and bigger. I mean, it can come down, I don't know, but it attains every value at every big value, or rather every value because continuous. Note it down, think about these questions. The integral is 0, okay? That is the, yeah. Or maybe as a first step, integral is 1. And then if you can, then 0 also you can think. Okay, so in particular, you understand unbounded function can on unbounded interval can have a bounded area. And don't just give me 0. Okay, obviously it's an unbounded function. Sorry. Yeah. Okay, note these questions, try them. So I'll put it here. And yeah. Next, I want to jump to a topic which looks very different. Okay. but let me do it. Let me introduce it as a problem only again. So, okay, please try those questions. Spend a little bit of time, try them. So what I want to do is linear functions. Okay. Now this is essential for us moving on. Linear functions uh, from R2 to R, or R2 to R2, R2 to R. Okay. Now we will be using these, like we will actually be using this in Euclidean geometry, or just the geometry. We'll do a bit of geometry, not much. We don't have time. So we'll do this. We'll be using this. But more for now, we will be using this in derivatives. And I'll just say a little bit why these are connected. And certainly this will give rise to the theory of matrices. That's the thing. And obviously we'll be using this in matrices and determinants theory, we'll know, and then equations and so on. Linear equations and so on, we'll be using them. So we'll be using them in several places. Yes. Mm-hmm. Constant function will not be unbounded. Unbounded, right? Unbounded. Otherwise, it's very simple. Otherwise, you can just take 0. But constant function otherwise will not work if it's not 0. Right? Let's see. Okay. So yeah. So let's just quickly do linear functions. Let's start with this a little bit. I'll ask it as an extension of a question which all of you would have seen in functional equations. Right? So, and we will not solve this question. I'm just giving it to you as a, you can use as motivations from here. F is a function from R to R, and f of x plus y is equal to fx. In the simple case, this is given, and it's given that f of cx is equal to c times c times x. No. What am I saying? Then everything is given, right? Yeah. F of cx is equal to c times fx. Or yeah, I mean, yeah, just keep this. Yeah, sometimes some more difficult versions are given, like continuity and so on. But all of us, you would have seen this question, right? And the answer to this is, yeah, fx equals, yeah, it's called the Cauchy functional equation, is something like this, or yeah. Okay. So this is what a linear function is. Okay, I didn't say how they were related in those things that you were saying, but let's just do it as a problem now. We'll see. I think we have enough energy to do it without context, right? Okay. So fx equal to f of 1 by. We know this is called a linear function, right? It's called a linear function. Linear function. Why is it called a linear function? And this is a small question. This will. How does a function represent a line? I mean, in what sense? I know it maybe does. It does, but. So you're saying it represents a line. That's right. So it represents line through the origin, and also if you look at it as a polynomial, then it's a linear. That way also, right? But yeah, linear actually comes from the line, so it represents a line, you could say. But does it function like something linear? Like as a function, why is it linear? Okay, yeah, right. That can be said, yeah. But another interesting way to put it is that if you input a line, then the output will also be a line. You can check this. Input some any other line, and the output will also be a line. Meaning that if you take inputs from a line, then the outputs will also come on a line. In some sense, these are the only functions that we understand, right? That's why we have derivatives, right? We try to understand complicated functions using the tangent lines. But yeah, this is just a. Let me then ask a question based on this, which you can think of. If, and this is probably very simple, if f is a function from R to R such that, okay, f of any line is a line, then no, not from R to R, it's from R2 to R2. I'm sorry. Okay. So then I think I am not making much sense, right? Yeah. So when I said earlier that, so just forget it for now. 1 second. Sorry. F, when I said here that f takes a line to a line, then what did I mean here? I mean, f is a function from R to R, right? So then, yeah, that doesn't, 1 minute. What am I saying? 1 second now. Sorry. Yeah. I mean, all this will make sense from R2 to R2. So yeah, then just dump this question, leave this question. Sorry. This will make sense after what I say something more. Yeah. But now the question is, if we just copy this question, but just make it from R2 to R2, maybe some of you would have thought about this. Okay. Such that now, if tuples of numbers, you can write this as vectors. Okay. You can write it in any way you want, but maybe we can just keep it simple. Takes in pairs of numbers, and this goes to pairs of numbers. Then how do you describe these kind of functions? I mean, we understand how to describe when it's from R to R, we know it is that. But how to describe these functions or give examples, at least some don't just the identity function, but give some examples. Remember, it's from R2 to R2. So the input comes from the plane and the output is also in the plane. So it takes in 2 inputs, you could say, and gives out 2 outputs. If, yeah, that is one way to say. It goes to x1 plus x2 comma 0. Sorry, I didn't understand. F of x1 comma x2, you're saying. Why would you put that? Okay, this is going to, yes, okay, like this you're saying. This is certainly correct, yeah. But this can confuse people. I mean, it can be confusing. So let me just write y1, yx2. Anything, but yeah. So the question is, maybe give examples and describe them. Like, can you find the functional equation problem, right? So describe them, describe, or maybe give examples. Yes, identity function. That is certainly true. Identity function, that's identity, yeah. That doesn't do anything. Preserves the identity of the input. Exactly. Okay. F of x1 comma y1 goes to and okay 3. Yeah, so these kind of things, scaling, yeah, the scaling, this is certainly true, but uh, minus plus you can do, yeah, that will also work. But any other interesting examples? And then how to describe log? But how will log take two inputs? But what was the idea behind saying log? No. See. This is all plus. Yeah. Okay. It's all plus. Yeah. Yeah. So now this is something that you all would have seen, but maybe you would have not thought in this way. Maybe is that matrices are such functions. I mean, I could say complex numbers and then rotation and reflection and so on, and you can understand. Complex functions are basically functions from R2 to R2, and the linear ones, the natural complex functions, which you can think maybe will be linear, the simplest ones, right? But matrices are examples, right? Clear. Matrices are examples. Matrices are linear, right? Can anybody say that why that is true? If you have a matrix, right? First of all, it's a function, right? Matrix, don't see a matrix like a static array, four things written. No, it's a function. And this view is essential in the theory of matrices to do problems, good problems. That a matrix is just a function, and it will take this x1, x2. It's a function that takes in x1, x2, and then gives you this number. But can you check that it is linear? If this is A, and you can just call this, you can just let's write it in bold. For now, we can call this pair of numbers as a number. Now this is linear, and all of this is the property of matrices, right? This is a linear, so A is the F, right? And we know that, I mean, we all know these things. This is A of X, this is the problem, right? So I'll just change it. I'll not call it X1, obviously. And so on, the properties, you can check. Yeah. So does everybody agree that matrices are examples? Okay. All right. Now, the task is to prove that these are the only examples. Meaning that any function from R2 to R2 which satisfies these properties, it is nothing but just a matrix. Meaning it will, you can think of it like it will function just like a matrix. There will be a matrix which will do the exact same thing, the exact same input output. Okay, this is the thing. Any ideas how we can prove this? We will not do this today because today I have to end 9. So 9 we end today. But any ideas how we can do this? Yeah. So remember, in the initial problem, it was fx equals to some c naught x, right? Where it's from R to R. And when it's from R2 to R2, then it just becomes fx equals to a times x, which is x is now not a number, but it's our new number. That's a matrix. These are the, so numbers are a language that helps you to capture these simple processes from R to R. But if you want to capture similar simple things from R2 to R2, then numbers are not enough, but you need 4 numbers at a time and some rules for handling them. Then you can use the same language for numbers, and the same representation works. Any ideas as to how you can prove this? How would you figure out a matrix that does the same thing? So can anybody come up with a matrix for this function right here? And then you can use your tactics of Cauchy functional that you had used. But first, can you quickly figure out a matrix for this f? So let's call this capital F. So this one here at the corner. Okay. Can you figure out a matrix for this? What is the matrix? What is the matrix of F? So you can just figure it out, right? You can just assume that there is a matrix and you will be able to figure it out, right? Think about it. I'd rather that you spend some time on this and do, okay? All right. It's a little bit new, right? But you see, it is a function. Exactly, right. But you see, it's a function, right? So yeah, it's a new thing, and but yeah, it's a function, and yeah, that's why you have to try to figure out how this is a matrix. Okay, figure out a matrix. So maybe that's the first exercise that, yeah. So first try this exercise, and then I think slowly we can develop. Yeah. Okay. Then we will see how this can be used in everywhere. Okay. We'll see. For matrices, yeah. So I mean, unfortunately, matrices are usually not seen as functions in class 12, right? That is a problem. So there are obviously books that you can read. So there is this book by Hoffman and wait. No. But there's a very simple thing that you can read if you want. So there is Artin's algebra. Yeah, I forgot this can be done. Yeah. Artin's algebra, I think first chapter he has matrices and he sees matrices in this way, I think. Yeah. So you can read that. Artin algebra and for chapter number 1. Yeah. But again, the problem is the language might be a little technical, but you can see. Okay. Try it if you want. Yeah. But think about these questions first. Also, these will give you the intuition. Okay? Yeah. And maybe also you can try this one, that if A is a matrix, if A is ABCD, then A of a line is a line as a function. So you can just take examples and try. Okay, and just take some matrices on your own and see what kind of functions they're giving. Identity one, then identity with flipped rows or flipped columns, and you will. Okay, and try them. I'll continue next time then. Okay. Okay. Thank you.